Hello, my name is Remy Gadou, and I'm bringing you the Pratt & Whitney sponsored project that I'm working on with Michael Maceda, Mohammed Al-Matari, and Professor David Giblin. A Chladni plate is a vibrating metal plate that deforms in complex symmetrical patterns when vibrating at certain frequencies. The purpose of our project is to use one of these to better understand how increasing the torque applied to bolts changes the way a system vibrates by attaching ribs to one of these plates. Pictured on the right, you can see our lab setup for measuring the displacement of a plate using accelerometers. Part of this project was creating an analytical version of our plate for comparison's sake. You can see on the left an ANSYS prediction of a mode shape of the plate at 1007 Hz. The nodal line is an area of a plate that doesn't vibrate along with the rest of the plate, as you can see by the stagnant sand on top of the plate. ANSYS can also be used to generate an amplitude plot for the plate's harmonic response.
Hello, my name is Michael Maceda, and for this project, the method that we use to solve for damping is called the half-power method. Q is the quality factor, and zeta is the damping coefficient. The Q factor is equal to the frequency at the peak divided by the frequency at the bandwidth. The damping ratio is then found to be 1 divided by 2 times the quality factor. The 3-bolt preloads that we will be using for this project were found using the tensile stress area of the bolt. Using grade 5 steel bolts with nylon insert lock nuts, we calculated the ultimate yield strength of the bolt to be approximately 44, 88, and 110 pound-inch. This is for 30, 60, and 75% yield strength of the bolt.
Hi, I'm Mohammed, and these are some of the graphs we obtained from our modal analysis in MATLAB. The following graph represents the first 5 natural frequencies. This was a sweep range from 30 to 650 Hz, and it was done in 100 seconds. The following graph demonstrates a comparison between two plates, one without stiffening ribs, illustrated in the blue line, and one with stiffening ribs, illustrated in the red line. As shown in the graph, the addition of stiffening ribs has a significant impact on natural frequencies. We can see that there's a shift in where the natural frequency occurs, as well as a decrease in the amplitude. From this, we can conclude that the addition of stiffening ribs indeed has an impact and an effect on natural frequencies. The final graph I want to talk about illustrates a comparison between the 3-bolt preloads that we used to tighten these stiffening ribs. The blue line illustrates 44 pound-inches, and the red and yellow one illustrate 88 and 110 pound-inches respectively. As we can see from the graph, as we tighten these bolts down, we can see that there is a dampening effect. There's a shift in natural frequency as well as a slight change in amplitude. As we double the preload from 44 to 88 pound-inch, we can see that a significant change in natural frequency and amplitude. However, as we increase it by 15% to 110 pound-inch, the dampening effect becomes smaller.
The data in this table is for the plus-shaped rib configurations at various bolt preloads. The table shows the results that we found for quality factor and damping coefficient. When the damping coefficient is less than 1, it means that the system is underdamped. When the damping coefficient is more than 1, the system is overdamped. From this, we can see in most cases that as the preload increases, the quality factor also increases. As a result, the damping will decrease because it is inversely proportional to the quality factor. From this, we can see that there is a correlation between bolt preload and damping. In conclusion, our team is able to determine how bolt preload will affect the damping of the Chladni plate. The second part of this experiment includes a study of damping for different rib configurations. Our team also developed a stiffening rib that borders the perimeter of the plate. However, due to time purposes, we only showed the results for the plus-shaped rib configuration. Using the same procedures, we can calculate the damping coefficient for both rib configurations and compare the results. Thank you all for listening, and have a great day.